So we're going to look at just a review of solving linear equations. Okay, so how do we go about solving linear equations? And this applies to some other equations too. It's not just linear equations, but in this case, we're talking linear equations. Let me have everybody click all your Chromebooks all the way closed. Get focus up here. So there are some basic steps to follow, and they talk about in your notes here the basic steps. They describe the steps this way: distribute, simplify each side by combining like terms, move the variables to one side, and then solve using inverse operations. And that's fine. I mean, that's an okay way to think about it. But I think there's maybe a more efficient way to think about it, and that's just with PEMDAS. Okay, if we look at our order of operations tree, there's a ton of stuff we get out of algebra from this really simple concept. We've already talked about how to simplify using order of operations. Now, when we're trying to simplify something, we just start at the top and work our way down, the traditional direction for PEMDAS. Okay, but when we're trying to isolate a variable, we do the opposite. We use inverse operations, which reverses the order of the PEMDAS tree. We start at the bottom and work our way up. So when we're using order of operations to solve, really there's two parts to this. Part one is we're going to simplify if necessary. It may not even be necessary. We're going to simplify until we get a single variable that we can point to on the paper, or I can point to on the board. And then once I can point to a single variable, then we use inverse operations to isolate it, right? How familiar are you with, is this, like, give me 1 to 5 on this. Is this making sense? You remember talking about this like in Math 1 and Math 2 quite a bit? Okay, good. So this should be, probably this will be an easier assignment, I would think, maybe than the last one, a little quicker. The simplification stuff, when you start using first that order of operations to simplify, in some cases there's quite a few steps there. So let's look at some examples. What about this one? We're going to solve the equation. So first thing we have to ask ourselves is, can we point to a single variable there? Thumbs up or thumbs down? Okay, now I'm saying a little bit of both. Let me define that. I'm not saying a single type of variable. I realize there are only x's in this, but I'm talking about a single actual variable. So it's thumbs down because there are two of them. There's one there and one there, right? So if I can't point to a single variable, I have to simplify. I've got to go through regular PEMDAS to simplify. Well, by order of operations, what's the first thing I need to do here to simplify? Say it again. Okay, I'm going to look in the parentheses, and inside the parentheses, x minus 6. Can I combine those? Okay, so there's nothing I can do in the parentheses. They exist there. So we could move on down the list. No parentheses. Are there any exponents? No. Multiplication. Aha. Is there multiplication? There is. What do I have to do for multiplication, Tayden? There you go. I have to distribute that 7. The 7 is being multiplied by this whole quantity. So the first thing we're going to do is we're going to distribute that 7 to both parts. So I get 7x minus 42 equals 10x minus 78. Good. Then we move down to the next step, which is addition and subtraction. Okay, what am I going to do there? Okay, good. I want to move the x's to one side or the other by adding or subtracting. In this case, that's exactly right. We want to push the x's to the right. And you can almost think about this like, oh, I don't know, you almost think about it like some kind of an animation or something. We're just going to be moving things around and isolating that x. We want to push the x's to the right this time instead of the left. How come? Why is it better to move the x's to the right than the left? It would work both ways, but it's better to move them to the right. Okay, good. So I get a positive coefficient of x. I always want a positive number of x's, right? So to accomplish that, I'm going to move the x over to the right, and I do that by simply just subtracting 7x, as you all know. So the x's cancel on the left, and now we're in a good place. Now we've got negative 42 equals 3x minus 78. Now we've hit a milestone here. Now I can point to a single x, and if I can point to a single variable, I can isolate it using inverse operations. So here's my single variable. Now we're going to work our way up and isolate the variable. Solving for a variable is exactly the same thing as isolating the variable, okay? So what's the first thing if I'm going to use inverse operations? I'm starting with adding or subtracting. What would I need to add or subtract to both sides to get that x by itself? Plus 78. Okay, good. Now I want you to think about this. This is there's going to be a motivation sometimes to maybe do some things. Well, how do I say this? I won't say too much for now, but we'll come back to this idea. Every step I make when I'm using inverse operations should accomplish something useful. Every step should be getting one step closer to getting the x by itself. So every step is going to move something away from the x's onto the other side, right? So the first step was add 78. So there's step one. Okay, if I do that, we get negative 42 equals, well, sorry, we get not negative 42. I have to add my 78, don't I? What's negative 42 plus 78, somebody? Positive or negative? Positive 36. There we go. Where's my, excuse me. 36 equals 3x. Next step, divide by 3. So we move up to multiplication division, and we divide by 3, and we got it. So those guys cancel, and I get x equals 12. Okay, now if I were taking a test, on the test, we don't want to just think it's right. We want to know it's right. So how could I check this to verify that I got it exactly right? Yeah, I could go back to the original equation and plug the value in, and it should satisfy the original equation, which means to satisfy an equation means to make it work, makes it true. So if I were to do that, if I were to take that 12 and plug it back up there, what would I get? I'd get 7 times 12 minus 6. What's 12 minus 6? 6. So 7 times 6 is equal to 10 times 12 is what, 120? Okay. Minus 78. Well, 7 times 6 is 42. What's 120 minus 78? 42. So it checks. Okay. Give me 1 to 5. Is that making sense? Okay. Let's look at just a couple more quick examples. What about one like that? What would I need to do first? I cannot point to a single x, can I? So I have to simplify first. What would I do to simplify here? Okay, I got to multiply the 3. Good. So that's giving me 6 minus 15 plus 30 equals, and how about this side? Okay, good. I'll distribute that negative 1, and I get negative x minus 6. I can simplify, like over here, this is kind of nice. The negative 15 plus 30 just combines to a plus 15, right? Okay, which way am I pushing the x's this time? Left. Good. If I do that, if I push the x's to the left, how many x's am I going to end up with on the left side? Going to be 7, isn't it? Because I'm going to have to add x to both sides to cancel that. So I'm going to get 7x plus 15 equals negative 6. Okay, look, now I can isolate an x, right? I can point to a single variable so I can start to whittle things away and isolate it. What would the 2 steps be in order to isolate that x? What would I do first? Say it again. Subtract 15, good, and then divide by 7. Everybody good with that? Okay, so we would just Subtract 15. So I get negative 21. I divide each side through by 7. And what's negative 21 over 7? Negative 3. And then we would just check it in the original to see that it works, right? Okay. Now I get on the homework, you're probably not going to check every one of these. And that's okay. I mean, because you can reload it if you get, but on the test, you see the value. I would take at least 1 or 2 on each homework assignment and just get used to it. Practice checking it just so when it comes time for the test, you've done it enough that you're comfortable with it. Okay, what about this? Now, here's what's different about this problem, and probably what makes it look a lot uglier than the other problems. Fractions, right? Fractions are difficult to deal with. They're cumbersome. So there's a great trick. It's called clearing fractions. It's very useful in the situation where you have a sum of terms on both sides of the equation. Okay. Now remember, we talked earlier about what does it mean to be a term? Terms are things that are added or subtracted, right? Factors are things that are multiplied. So how many terms are there on the left side of this equation? This rate, you can just show me with your fingers. How many terms are there on the left side? Okay. I'm seeing a couple different answers. If I'm seeing some 2s, which is correct, and I'm seeing some 1s. People that have, does anybody want to explain why? I mean, what's the motivation for the 1? How many things are being added or subtracted on the left side? Doesn't it look like I've got, here's term 1. 1/6 x is one term plus 7. There's a plus sign there, right? That's separating those two terms. So I got 2 terms on the left side. Now let's try it on the right. How many are on the right? 2. There we go. Okay, so total of 4 terms. Clearing fractions works when I just have a sum of terms on both sides, and that could be adding or subtracting terms. Notice there's no multiplication going on other than just the 1/6 times the x. Inside the terms, it's okay if I multiply a number times a variable or something, right? But nothing's being multiplied or distributed on both sides, right? So this is a case where we can use this technique of clearing the fractions. Here's how it works. All I have to do is I'm going to multiply through the entire equation by the least common multiple of all the denominators. In other words, it would be the common denominator of all the fractions. Well, what's the common denominator of 1/6 and 1/3? Or, a 6's and 3's on the bottom. So what's my common denominator going to be? Is it 3 or is it 6? It's 6. How come? There you go. Okay, very good. So the least common denominator, which means just the least common multiple of the denominators, that is just the smallest number that all of the denominators will divide into equally, right? 3 divides into 6 evenly, but 6 doesn't divide into 3 evenly, does it, right? So it's 6 in this case. So if the LCD, the least common denominator, equals 6, then this is all we do. We're just going to multiply a 6 or a 6 over 1 all the way through. Okay. Well, if I distribute the 6, what's 6 times 1/6? 1, right? Because it's the same thing as multiplying 6 over 1 times 1 over 6. We multiply fractions straight across, don't we? Right? So that's going to give me, when I distribute to that first term, I'm just going to get 1x. 6 times 7 is what? 42. And then over here, we got to distribute the 6 to the 1/3. Okay, 6, I'm going to multiply straight across. So I'm going to get 6 times 1, or 6 on the top, 1 times 3, 3 on the bottom. 6 over 3 reduces to 2. Okay, and I've got an x there, right? And then finally, I'm going to distribute that 6 over to the 3 and get an 18. And now that's easy, right? Look what we did. Now we just bought a problem by clearing the fractions. We turned a hard problem into a really simple problem. We won't even finish it. I mean, you guys can all finish that, right? Push the x's to the right side, solve for x, no big deal. Okay, let's try another one. Okay, this is a little tougher. Got bigger numbers in the denominator. So again, I'm looking for the least common multiple of all the denominators, the smallest number that all the denominators divide into evenly. What do you think it is? You got an idea? 20, well, let's check it. 20 works for 20, it works for 4, it works for 5. Does 8 divide evenly into 20? No, so it's not 20. What is it? Oh, no. Maybe I got to suggest. Yeah. Okay, now what's the easiest way to find 40? We're trying to find a least common multiple. So let's start this off by just looking at a list of multiples of all the denominators. Okay. When we say multiples, you know what I mean. We're starting with, 1 times 20, 2 times 20, 3 times 20, etc. Those are the multiples of a number. Well, the first common multiple, common means shared, right? So the first time we get a common or a shared multiple is 40. Well, there's 40, there's 40, there's 40, there's 40. Which list of multiples is probably the easiest one to work with? The 20, yeah, because the steps are really big, so I have fewer multiples before I get to a common multiple. So a good strategy is always to see what's the biggest denominator and then just work my way up that list of multiples until I get a winner, one that the other numbers divide into, right? So in this case, it's 40, okay? So does that all make sense? Give me 1 to 5 on what I just said, right? Start with the big denominator and look at the multiples of that one until you find one that works. Okay, now I'm going to show you another really good trick here. So when we multiply this 40 through, 40, I could make it 40 over 1 if I want to. When I distribute that all the way through the whole thing, I'm going to get some pretty big denominators, aren't I? Right? Like if I multiply straight across, 40 times 5 is 200 over 1 times 8 is 8. What about this one over here? Yikes, if I multiply 40 over 1 times 17 over 20, that's a huge fraction, okay? Those are going to be kind of difficult fractions to reduce. In the last example, they were simple. I mean, we ended up with like 6 over 3, no big deal. But in this one, we get these enormous fractions that we're going to have to simplify. So we got a trick. Think about this. Rather than distributing first and then reducing this big fraction, we handpicked this number 40 because all of the denominators divide evenly into it, right? So why not be really smart about this? Why not first reduce 40 divided by the denominator, and then after I reduce that fraction, whatever I get, multiply it by the top? Isn't that the same thing as multiplying first and then dividing by 8? Why not divide by 8 first and then multiply? So what is 40 divided by 8? 5. So let's cross out the denominator. And whatever we got when we reduced, we'll just multiply that by the numerator. What a great trick, right? So then we end up with 5 times x is 25x. 40 divided by 5 reduces to what? 8. So we'll cross out the denominator and we'll multiply that 8 by the numerator. 8 times 3 is 24, so I get a minus 24. 40 over 4 reduces to 10. So I'll cross that out and multiply 10 times 3 times x is 30x. And finally, 40 over 20 is 2. There you go. And 2 times 17 is not so bad. That's just 34. Now look, we got an easy equation, right? Okay, will this always work? Yes, it will always work to do this trick when you're clearing fractions. Now, if I weren't clearing fractions, what if I were multiplying by 27 out front or something? Well, that's not going to work. If it's just some random number, we don't know that all the denominators divide into it evenly. So in that case, I would have to just multiply straight across and reduce. But when we're clearing fractions, remember that we are picking that 40 specifically because all the denominators are going to divide into it evenly. So when you're clearing fractions, you can always do this trick. Okay, how much time we got? Okay, well, we'll practice that. I was going to do some board work. We'll do that tomorrow. Okay? All right, I'll put the assignment up. You can get a jump on it, but I won't make it due until, let's see, won't make it due until the Tuesday after break. Okay? So get as much done as you can, but if you have a couple lingering questions after a roundup, you can ask them on Monday.